when you reconstruct force fields with machine learning, conceptually it's a very simple process. So the first step of this two-step process is to generate the data, and usually you would want to generate the data on a very high level. So you would like to have highly accurate reference data, as accurate as you can afford. So because you need to compute several of those data points along the potential energy surface in order to assemble a good reference set. And then using the data, you choose a class of functions. So you choose a parametric function class that fits your data. And it's very easy to define a function class that is that yields a so-called universal approximator, which means that in the asymptotic limit, if you add enough data, you can actually fit this potential energy surface perfectly. But obviously in practice, the asymptotic limit is not good enough. So what you would like is you would like to select from a function class that is constrained to follow the basic physical principles, right? So for example, symmetries like invariances or equivariances, you would like them to be included within this class, right? So that you effectively choose from a smaller set of functions. And this way you can maximize essentially you want to get a lot, right? A good representation from a few reference points. Now,
the class of your models is models with a lot of parameters or not?
Yeah, they usually have a lot of parameters. A lot of parameters. So it's a very empirical approach.
If you have a lot of parameters, you can always fit.
That's right. That's right. And this is the challenge, to find something that has, so the challenge is to find something that fits well. And actually, if we go to highly nonlinear models, then this idea of over-parameterization becomes a bit complicated. It stops being a problem, like it is in in the linear regime. But this is, just a side remark. So, those models are very complicated. They have many parameters that are highly empirical. But still, the fundamental physics helps a lot to actually get a good representation. So the better your representation is, the more accurate data you can afford, and therefore you can really realize your ultimate goal of this whole process, which is to take a small amount of data and then bootstrap it into a model, and then use this model to perform long timescale MD simulations that effectively are at the same accuracy as your reference data, right? So for example, with coupled cluster, you could do an MD simulation. You cannot afford to do a full ab initio MD simulation, but then by using this machine learning approach, you could do it. Now, the problem is that both of those steps, so the data generation and the model selection and the model creation, they are held back by the same fundamental scaling law, which is the number of interactions that you have when many particles interact, right? So this exponential scaling during data creation is in terms of the electrons. And then here on the machine learning side, we have a bit more favorable condition, because here we adopt this atomistic picture, which is a coarse-grained representation effectively. And in this atomistic picture, there's less things that need to be coupled, and then which means that with machine learning we can scale a bit more easily. But then here we have to deal with we're dealing with a whole set of data. So this is at least a linear factor on the complexity of this guy. Okay, so let's look at the scaling. So in the easiest and the most simple scenario, you only assume a two-body correlation. And then we still keep this atomistic picture here. So obviously everyone knows what a quadratic function looks like. But just to illustrate this here, if you have a small system with 40 atoms, then you have around 800 interactions, and then you multiply this by 10, so you end up at roughly 400 atoms, and then your interactions within the system increase by 100-fold, right? So you can easily see that this scaling law quickly becomes a showstopper, even for machine learning models that deal with only with the atomistic degrees of freedom. So what people do is what they do is they, in reference to Fabian's talk, they use a chemistry trick, which is they localize. So this is an example. Consider this little test system. Here we have a delocalization of electrons, and then when we turn this rotor, what you were seeing here, we can run it again. What you see here is the contribution of each of the atoms to the overall energy. So you have positive and negative contributions. Obviously, this decomposition is completely arbitrary. This is one result of a model, of a global model, that considers all of the degrees of freedom. Now, this is very expensive, obviously. For such a small system, it's okay, but that prevents scaling up. So what most machine learning models do is, and there's a very faint rest of the molecule that you cannot see here, but what most machine learning models do, they look at local neighborhoods, right? So they only consider the full interactions between atoms within those local neighborhoods. And then what they get is two very useful advantages, which is the parametric complexity obviously decreases because you have less interactions to parameterize. And arguably most importantly, or also important, is the transferability increases. So those little fragments, if you're lucky and they reappear in certain places in your system, you can reuse what you learned in one area and then transfer it to the next. So they do this for atomic environments, so for all of them in a system. And then in order to still have some notion of global interactions between those systems, there's usually some kind of a mean field interactions that most models allow, right? So for example, message passing schemes are one way to impose this, to allow this mean field interaction, where they are low dimensional, right? So some kind of reduced messages sent between those fully correlated neighborhoods. Another way to do this is in linear methods, for example, what they do is they use descriptors that are that capture the global structure, but they are not parameterized. So there's no parameters that can be learned. So it's also a downfolding approach effectively. Now, so this localization removes important degrees of freedom. And if you only look at the test errors, which people usually do in benchmarks, where they benchmark machine learned force fields, then this locality is not a big factor because the global interactions are a small fraction of the overall energy, right? So the energy error can be low when you adopt this locality approach, which is a good thing because that means that it works. But if you look into the asymptotic regime, for example, or in the extrapolation regime of the data, then this lack of global interactions can become a problem. So here is the same example again. This is the same molecule that you saw in this animation before. And now we look at two different models. One is a global model. I will talk about this particular model in the later part of the talk. And then the other model is called SGDML. It's a very popular message passing network that is very accurate, but it imposes a local cutoff. So it uses this very popular approach of localizing interactions. And then you can see here for this energy profile, which is the result of turning this rotor, as you saw in the slide before. You can see that if you choose the cutoff small enough, then the prediction completely degrades here. So the energy along this profile is not being predicted accurately for this local model. And you have to increase this radius, so that the local neighborhood, which obviously then also increases the complexity, to almost cover the whole molecule in order to get this profile somewhat right. Whereas the global model doesn't have this problem because it doesn't impose localization. Yes?
So in principle, you can add as much non-locality as you want by just adding more layers, right? So with SGDML, you also have the problem that you only have two correlations in there. Would that equally be an issue here?
Right. So by adding layers, you can essentially propagate information beyond the cutoff, and by adding more and more layers, you can propagate it further away. But this is essentially a diffusion process, right? So if you choose a small cutoff and then try to compensate by adding more layers, then you will run into the problem of this information that you want to transmit diffusing.
Some of the information from one, as you go through layer to layer, you lose the
Right.
information is more and more averaged out.
Exactly, they average out.
And sometimes that's exactly what you want, but you say no.
Well, I mean, so it takes care of some of the it takes care of some of the interactions that you want to have in a long distance. But if you have explicitly parameterized interactions, you can be more accurate. And this is actually exactly what happens here. That some of the or like, well, in the interpolation or extrapolation regime in general, where this doesn't work anymore.
Do you have any sense for this problem? Like, in addition to this locality, what kind of problem is induced by not having angles? Right, like Schnet is just distances, right? There's no direction.
Yeah.
I think that's what you
That's
also.
That's exactly what I was wondering.
Ah, okay.
Yeah. So if you use N instead of Schnet, does it change?
So it's true that so the Schnet is based on two-body interactions, so on distances alone. In principle, you could add higher order interactions, and actually this is something that we do in this model. But any higher order interaction, eventually the higher the interaction is, the higher the exponential cost of computing all of those interactions, right? So angles, for example, are more expensive than just pairwise distances, and so on. And yeah, so the angles would take care of some of it, but not completely alleviate the problem, unless you allow yourself to run into, into this exponential cost regime.
Yeah.
I have a question here.
Yes. Can you hear me, Stephen?
Yeah.
Are there parameters that are particularly robust to a shorter cutoff besides the energy?
You mean like whether properties that are where a local assumption is?
Exactly. If you can have a shorter cutoff and get as good results with other observables.
Right. So I mean, even for the energy, a local model is breaks down in certain scenarios. That, but not. I mean, it's not a general. It's good enough, right? Because you can always, there's a sweet spot. So this is a hyperparameter, and what people usually do is they optimize this cutoff radius, until they can accomplish whatever prediction task they set out to do. So even for the energy, this is not this is not completely this is not preventing you from reconstructing force fields. But just in this is certainly a problem that needs to be taken care of if you want to scale to really large systems, because then at some point, at some scale, you eventually run into problems.
So there's no, as far as you're aware, any relative advantage with other observables and having shorter cutoffs for this kind of local interactions and capturing the phenomenology good enough?
No, I mean, if the property is it's conceivable, obviously, that whatever. I mean, I'm not. Yeah. So there might be some properties where this local cutoff can really, only has advantages, but I'm not aware of any right now.
Okay. Thank you.
Okay, thanks. Okay, so going back to the scaling, there's one surprising. There's one interesting fact that is kind of surprising to me, which is that for a global model, obviously you need global reference data as well, which means that you need to you calculate reference data using ab initio methods for large systems. And I always thought that this is the bottleneck, right? So that at some point we cannot really compute this global reference data anymore. But it turns out that it's not, right? Because DFT actually scales to a few hundreds of atoms, and then the global global models, global machine learning potentials, they actually are stuck with stuck to system sizes of less than 100 or about 100 atoms. So really, the data is there. We just need to develop those global models to populate this regime of system sizes. So this is what we are going to do today. So we're going to fill this gap by making global models scale such that we can treat all of the interactions using the same simple model without any additional corrections. And we adopt two approaches, the first of which is rather straightforward. So we take a model that already is global, but has scaling issues. Those scaling issues are usually due to the coupling of this high number of correlations within big systems, and they lead to numerical issues. So the first approach is to alleviate some of the numerical issues to make them, trainable basically on computers. And then the second approach is to be selective about global interactions, so that we can, we don't have to a priori cut the interaction range of our model, but we enter the problem with the assumption that everything correlates, and then we just select the most important ones. So people have been working on this before. This is a problem that has been recognized. This, non-local effects, how to incorporate them into machine learning models. And again, they use something that has been known in computational chemistry, where they try to formulate, they try to fix the asymptotic behavior of this local machine learning potential by imposing a correction term. So here, in this case, I borrowed this figure from a recent paper of a colleague of mine, Oliver Unke. And what he did is he took a local potential, and then added correction terms to make sure that it behaves correctly in the asymptotic term. But as we have heard in many talks this week, the long-range correlations between electrons, they're very complicated, and it's not really a well-defined problem how to correct for those interactions. So this works to some extent, but obviously the ultimate goal would be to have just the data set and then one model which absorbs everything. And this is just a small selection of very similar approaches where you always have a combination of two models for long range and for short range. Sometimes, the long range are fixed corrections. Sometimes both of them are learned. So this is a very active field. Okay, so going to the first section, how to improve numerics of a global force field. So we will base this on a force field that we introduced a while ago, and partly it has been developed at one of the IPAM long programs as well. It's called the Symmetric Gradient Domain Machine Learning Model. And this model is a global model. It correlates all the degrees of freedom in a system, but it's applicable so far only to small atoms, up to a few dozen, small molecules, up to a few dozen atoms. And we have used this. It's very accurate, very data efficient, because it's endowed with many physical priors. So we have used this to train coupled cluster data and then run quantum MD simulations based on those coupled cluster force fields to get observables, like, for example, free energy surfaces or vibrational spectra. And using this combination of a highly accurate coupled cluster force field prediction in combination with path integral molecular dynamics, we've been effectively able to run MD simulations with fully quantized electrons and nuclei. So the problem with this model is that it doesn't scale. It's very data efficient, this model. And this data efficiency comes from the fact that it's endowed with many physical priors. The most important one is energy conservation, which allows us to, so we take this model is based on a Gaussian process. We take this model and we train this model in the gradient domain, which allows us to train on force samples instead of energy samples to reconstruct a force field. And force samples, they can be obtained analytically at a lower cost than the finite difference set of energies, the equivalent finite difference set of energies, which means that this allows us to be more sample efficient. Another property of this model that we will leverage here is its linearity in the learnable parameters, which means that per interaction we have the lowest amount of parameters, which is just one parameter per atom pair. And then on top of this energy conservation, we added other strong constraints, like, for example, the exchangeability of equivalent atoms, so permutational symmetry, and then obviously rotation invariance and translation invariance and so on. So from a low number of data points, we can reconstruct an accurate force field, but we need to make this scale. And the reason why it doesn't scale is that it's numerically fairly unstable. So what people usually do to cope with this instability is they use matrix factorization schemes. Those are usually the most stable and most accurate. So they take this, it's a big matrix that we need to, in order to train the model, we need to solve a linear system. So this is why some people call it training, right? Because it's a very simple problem. So we need to solve this linear system. And in order to do that, we look at the properties of the kernel matrix here, and we factorize it because it's symmetric and positive symmetric in it. We factorize it using Cholesky factorization, and then this has a memory complexity of n squared and a cubic time complexity. Now the problem is that this prevents scalability, obviously. So the alternative would be to train it like a neural network and to just take the gradient of this of the cost function of this machine learning problem, and then just follow this gradient, right? So here, for example, this is the gradient of the simple linear problem, and we have a learning rate here, and then we just iterate until we converge our parameters. Now, this would never, the advantage here is that we only use matrix vector products, which means that we never instantiate the matrix, and therefore we avoid the memory scaling, which is the main bottleneck. Now, the problem is this would never converge because the condition number of k is horrible. So it doesn't even help if we try to be smarter about this iteration using Krylov subspace solvers, where we replace, so this would be the properties of k allow us to replace this learning rate by optimal learning rate according to a conjugate gradient scheme. And then this gradient step we can project onto orthogonal gradient directions, which again would give us, in principle, very fast convergence. But it's all limited by the fact that k has a horrible condition number, and the condition number is proportional to the convergence rate. And in practice, this would never converge, right? So here's an example of a typical example of the spectrum of a kernel, of a kernel. And you can see that the largest eigenvalue is very large. And then the kernel has a null space that we lift through this regularization, but the condition number is horrible. So we actually need strong preconditioning in order to tame this problem. And there's special challenges attached to this, because sampling this kernel matrix when it's very huge and when the kernel and the descriptor are expensive is very expensive. So we cannot use approaches that access k too often. So what we do instead is we use a preconditioner based on a Nystrom approximation of the kernel matrix, and which requires us to sample certain columns, a few columns from k. And this sampling, which columns are the most important ones, we determine by using a leverage score sampling scheme, which can be also expressed in a very efficient way. And then we obviously want to avoid instantiating this product here, because this is where the computational benefit comes from. So we need a preconditioner that looks like this. And we need to factorize it so that we can evaluate this preconditioner in every iteration effectively. So this factorization we do with a number of tricks, where we use the Woodbury identity in order to not instantiate this guy. And then here we need to factor it into 2 Cholesky factors, and this can actually be done without evaluating this very unstable square of a matrix here by applying a QR decomposition, and then which then gives us one of the, so the R actually is a Cholesky factor in this case, or it can be formulated that way. So this we do this in a very stable way. And then by choosing the number of inducing points in this preconditioning scheme, we can actually, from our initial memory demand of the closed form solution for this problem, and also the initial time demand for this closed form solution, we can then arbitrarily trade off those two resources to have, to any extent we want, right? So we can add a strong preconditioner, which is more expensive to compute and needs more memory, but then we converge faster with the overall problem, or we can choose a weak one, and then we need to iterate faster, and then overall, actually, we can be faster than the closed form solution in general, right? Which is really nice. So this enables us to scale our SGDML force field to intermediate size systems of a few hundred atoms, which was not possible before. So here is here's a very brief example of a few systems that now become possible. So they all have up to a few hundred atoms here, and then we can reconstruct force fields that are very accurate. So the forces here are well below chemical accuracy for all of them, and they are only based on a few hundred or a few thousand points at a maximum. And then here, actually, we plotted the global interactions. So here you can see the yellow atom interacting with all of the other atoms to assemble the force prediction, and then you can see that all of the atoms, due to the formulation of the model, participate in this prediction. So you can see here how it looks like, in a very, very short MD simulation. So it's not static at all. It's very complicated. Yep.
How many parameters do you have in these systems?
So in this linear model, we have 3n times m, and m is the number of training points, n is the number of atoms parameters. Yeah.
The number of parameters is what matters, because the cost of, for example, the QR factorization is mn squared. You can then really push this down with rank revealing methods and so on. So I'm curious, just what's really the limit? And so what's the n? What's the number of parameters?
Yes. Right. So it's, And so for this system, I don't know how, I think this 80 atoms. So 3 times 80 times, let's say, 1,000 points would be the number. So it's way less than neural networks would have for similar systems. So this is the trainable parameters, and then the matrix is that squared. Right.
Okay, I may need to get the numbers later.
Okay. So those models, they, due to the linearity and most of the magic, so to speak, is in the nonlinear kernel construction, which is fixed. They have less parameters than neural networks of a comparable performance. Okay, so those you can download. We have code for this. You can reconstruct your own force fields using your own data sets. We have code for this. You can, it's fairly easy to use. But now you can also just go to our website and then upload your code and actually get the force field directly. So we train it for you in case you don't have GPUs, for example, or need it quickly or whatever. And then you can use the same code to apply it in MD simulations, for example, using ASE or compute any other observables. So this really allows you to parameterize a small data set, make it usable in simulations. Okay, so this was on improving the numerics of global force fields. Now the other topic is to be selective about the interactions you want to model within the system. So this is more scalable potentially because we enter with the assumption that everything is correlated, but then we cut down on the interaction that we allow, right? So the scaling law, we don't allow it to limit the system size in this case. So this is work. Well, we accomplished this using so-called attention mechanisms, which allow what we call geometric routing of information between interacting particles. And this is work by a very good student of mine, Torben Frank. He will also be joining actually this long program, and then we can talk in more detail. but I will first give a brief overview today. And so he developed this. It's called GeomAt. So it's an attention module that you can use. You can integrate it into a bigger neural network, which is usually called the transformer. And this transformer architecture allows you to again reconstruct force fields, and it pays attention to those interactions in your system that it deems most important, which can be statistical correlations, but they can also be really chemically meaningful things. And here, for example, for this test system, we looked at the interactions that it extracted, and we can recognize for example, the covalent bonds or the hydrogen bridges, but also we have interactions that are just statistical correlations that still help the prediction, because ultimately machine learning models are defined by the data set. And most importantly, we have interactions that are completely, very small or gone completely, right? So that the model ignores and which makes it efficient. Now, first I want to give a brief overview of the attention mechanism and how it works. So originally this idea comes from natural language processing, which is why there are three terms that have been coined in that community, which is queries, keys, and values. So queries and keys in our case are just representations of atoms. So we always pair a query and a key, and then when this pairing is of a high value, they interact. If it's low, then they don't interact. And then values would be some message that this pair exchanges. So this is some generic information, right? And so, well, those embeddings or those values, those are vectors, high-dimensional vectors. They're extracted from atomic embeddings. I will not go into detail about how they are constructed, but those are representations of the atoms. So each atom of the same type starts off with the same representation, and then it's being refined depending on certain factors. Doesn't really matter at this point, but the interesting part is that from those representations, we have some learnable transformation. It can be a simple linear transformation, nonlinear, whatever, but it yields those queries and keys, and then during the training procedure, the network can determine whether it should relate some specific pairs within the system or whether it should ignore them. Now, this is accomplished through a very simple inner product. So we have an inner product between all of the keys and all of the queries, so all of the atoms in our case. And then it's being rescaled by a continuous version of a maximum, right? To really extract the important ones. And then we send the values using this weighting scheme. Okay, so this is a very high-level description of self-attention. And then what it means that for a system like this, you would, for example, get an attention matrix that looks like this, that contains the routing information, right? So instead of seeing the covalent bonds, our network, well, yeah, every one of those matrix elements is an inner product between the key and the value vector. And instead of seeing covalent bonds, this is what the network sees. So it extracts its own representation of interactions. And even in this example, for example, you can see that some of them are very important, and this might not be immediately obvious from a chemical perspective why the network deems them important. And here you can see for another system, again, we look at the interactions that the network extracted. And we plot them here as a function of bond length. And you can see that, over the whole, of a bigger data set, if you look at many of them, you can see that they're highly nonlinear, right? So it's not a trivial correlation that the network extracts. Now, there's a problem with the default definition of attention. So attention is a very popular mechanism. It actually replaces or generalizes this concept of convolutional networks or message passing in a non-local way, right? So convolution is being defined by its locality. Attention is the same general idea, but extended into a global context. And the problem is that it's coming from this natural language processing world. It doesn't, in its standard formulation, doesn't have any notion of geometry or structural dependencies, right? So since it only works with inner products, for example, we could not distinguish the distance between two atoms if we only consider isolated representations for each of those atoms as keys and values, queries. And so basically pulling those two atoms apart would always give us the same attention value. And this is obviously not useful if we want to use attention to reconstruct the energy, because the energy obviously would not be the same in this case. So what Torben did is he developed a scheme to fold this geometric information into the representation of the atoms using a density representation. So consider this test system here with 3 atoms for which we only know the Cartesian coordinates. He imposes or he interprets them as densities in space, uniform densities. They're all the same. They're all just RBFs, or just Gaussian functions on each of the coordinates. And then from this density representation, in order to determine the interaction, which then eventually yield the attention values, he looks at the overlap of the densities. So the overlap, it changes when two atoms are being pulled apart. And looking at the overlap has a very has an advantage over other methods, which is that you need to evaluate this overlap integral, which when you look at each of the interactions is still in its analytical form, and then you just need to you can define some integration scheme depending on how granular you need to evaluate this overlap, right? So here, he uses some discretization points and then interprets this integral as a Riemannian sum to evaluate the attention coefficient, right? So this attention coefficient in its standard formulation actually becomes this overlap integral. And there's 2 more important transformations here, W1 and 2, which can be also linear as shown here or more complex. But this is very important because what they do is they effectively transform this simple RBF structure that we initially put in for each atom. They can transform it into a much more complicated effective density. So now you have those very complicated densities interacting and giving you very descriptive overlap results. So then we can assemble this self-attention block into we can use many of them to make it wide, and then we can take this layer and then use many of them one after the other to make a deep network. And this allows us to, and then in every step we look at this, we generate an attention matrix like this, and then aggregate information according to this attention scheme, right? So this allows us to make the geometry determine the flow of information through our system, and then we do it over several steps. Yes.
So, are you dropping entirely the atoms as positions, and you're replacing them with the density, and you're basically taking the signal as input?
Well, so for this attention, to determine the attention coefficients, yes.
And then you do the transform, and then you get some representation, and you've already learned that, and you don't.
So this is to determine basically the coupling between each pair. Yeah.
You just take the density of every pair, or do you take like an actual global density? So if you do the integral between 2 points, you have a third point.
It's along a line. It's along the line that connects.
But if you had a third atom, like somewhere on the side, would it change the integral? Because there's like an additional density.
So the densities extend in space, but we integrate. For the pairwise, to determine the pairwise coupling, we integrate along the line, right? So one atom influences all the other atoms, but the overlap is determined between pairs, although this can be extended, which I will.
I think what Marcel was asking is if you have, for example, another atom between the two, you ignore that density, you just do the overlap between the 2 atoms you're currently evaluating. on the line, right? Then you forget about
Yeah.
all the other
Yeah.
Okay.
density contributions.
Thank you, both.
But this can be actually, well, this is the next slide. So what I explained so far is two-body correlations, where we look at the overlap of densities between two atoms. But then we can extend this to any higher order by looking at overlaps between overlaps, right? So for example, here for three-body correlation, we would compute this more complicated integral, and this way we can build up a higher order interaction scheme without relying on depth as message passing schemes do. Okay, so we evaluated this network on a very popular data set, which is the MD17 benchmark data set that has been adopted by many works, and so this model that we developed here is really a high performer in this benchmark. So that the purple dots here indicate the performance of our model versus all of the other models that have been tested on those data sets, on those respective data sets. So this is for the energy prediction task and the force prediction task, and this is an exhaustive set of results that have been published. So this is not cherry picked. The ultimate test, and this is the last experiment, the ultimate test of such a model is obviously to look whether it behaves in a predictable and stable manner in those troublesome regimes, like the interpolation regime. And for that, I would like to show this little experiment that we did. So we trained the network on a mixed set of structures from the QM7X dataset, which is a dataset that contains a wide variety of different molecules of a different size, and each of those molecules have been perturbed from equilibrium, and then you got energies and forces and other properties for those structures. And we took a subset of structures, trained the model, and then took a new structure that was not in the training set, and made the model relax that structure, right? So the model has never seen this guy, and it's not in equilibrium, and now we ask the model to put it into equilibrium. And the difficult task is that this structure in itself resides in the extrapolation regime of the model. And then also we perturb, for example, those hydrogens here, which means that they're definitely far away from the true equilibrium structure, and here's actually how much this input deviates from the true equilibrium. And now we put it into the model and then run a relaxation, and it yields this structure as our equilibrium. And then if we again compare this with the true structure, then we are extremely close, which means that it can handle this extrapolation task really well. Okay, so so this is already it. So to conclude, I've shown two approaches to scale to global to scale models so that they allow global interactions and local interactions at the same time. First of which is to just improve the numerics, and this is where we scaled the SGDML model using a preconditioning scheme and an iterative solver to large systems of a few hundreds of atoms. And I don't believe that, this is ultimately limited by the fact that it's a quadratically scaling algorithm. So for the future, we need to develop another solution, and we looked at attention mechanisms. So we believe that this could be the way forward to really large systems without adopting this localization ansatz. And this is something that needs to be developed further, obviously, to really approach the big systems that are really interested in. But it seems to be very promising. And again, I would like to refer you to our website where you can reconstruct force fields from your own data sets.